Today's lecture will be on whether or not we can predict the formation of a precipitate and which substance will precipitate first, given KSP expressions and KSP equations. The first problem that we have is up on the smartboard here. We have predicting precipitate formation. We are going to solve for Q. You remember Q from our previous unit in the equilibrium unit. Q values are for when an equilibrium is not at equilibrium. So we don't call it a KSP value, we call it a Q value. And then we will compare Q to KSP. If we're above KSP, then we have the correct amount of ions so that the ions will collide together and form precipitate. If Q is less than KSP, we do not have sufficient numbers of ions in our solution to form that precipitate. So our sample problem, we're going to mix silver nitrate with zinc cyanide and determine whether or not a precipitate will form. Let's give you a quick sketch about for what's going to happen in this problem, kind of a visualization, if you will. We have a container containing silver nitrate and a container containing zinc cyanide. We want to take those two containers and we want to mix those together. And the question that we're asking is, will the AgCN solid precipitate out? And that's our unknown, if you will. We start with 15 milliliters of the zinc cyanide and 10 milliliters of the silver nitrate. So our new total volume, our V2 if you will, is going to be 25 milliliters. So the first step of this problem is we need to figure out what is the concentration of these ions the moment before they start to potentially form a precipitate. In other words, we're going to dilute each of these ion concentrations as we mix these together to form a new concentration, and then that new concentration potentially will be high enough that those ions will combine together to form that precipitate. So first step to this problem, we need to write our chemical equation. We're going to look at the silver nitrate dilution. So silver nitrate is a soluble substance. It breaks apart into your silver ions and your nitrate ions. We will do the dilution formula, M1V1 equals M2V2. Our initial concentration of the silver nitrate is 0.0005. Our initial volume of that is 10 milliliters. Trying to solve for our new concentration, and our new volume is the 10 plus the 15 as it mixes for a total of 25 milliliters. We solve for M2 and we get a concentration of 2 times 10 to the negative 4th molar silver nitrate. Now the issue is we're not concerned about the concentration of silver nitrate. We want to know the concentration of the silver ions that could potentially combine together to form that compound. So I have to do a quick molar ratio using this balanced chemical equation here. For every 1 mole of silver nitrate, we are going to produce 1 mole of silver ions. So we're going to have 2 times 10 to the negative 4th molar Ag plus ions. We now need to do the same thing with the zinc cyanide. We need to do a dilution for that. So we have the zinc cyanide dilution. Process is very similar to what I just showed you. The zinc cyanide will dissociate into zinc ions and to cyanide ions. We're going to do the dilution formula, M1V1 equals M2V2. So our initial concentration of the zinc cyanide is 0.001 molar. We had 15 milliliters of that. We're solving for M2, and our new total volume is 25 milliliters. So we solve for M2 and we get 6 times 10 to the minus 4th molar zinc cyanide. Once again, we're not concerned about the concentration of the zinc cyanide. What we're concerned about is the concentration of just the cyanide ions. So we're going to have to do a quick molar ratio. For every 1 mole of zinc cyanide that dissolves, we are going to produce 2 moles of cyanide ions. And this is why that ratio is so important to us, because it's not always going to be a 1-to-1 ratio like it was for the silver nitrate and silver. In this instance, it's a 2-to-1 ratio. So we get an answer of 1.2 times 10 to the minus third molar cyanide ions. Now we're ready to go ahead and calculate Q. We recognize that silver cyanide, a relatively insoluble compound, is going to establish an equilibrium in its container of silver ions and cyanide ions. We then write our KSP expression, concentration of the silver ions times the concentration of the cyanide ions. I have calculated the initial concentration of the cyanide ions and the initial concentration of the silver ions. So I'm going to plug those initial concentrations into my KSP expression. 2 times 10 to the minus fourth and 1.2 times 10 to the minus third. But now, because they're initial concentrations, I now need to call it Q. I go ahead and solve for Q. I get 1.2 times 10 to the negative seventh. My KSP value given in the problem is 1.2 times 10 to the minus 16th. Therefore, Q is greater than KSP, and a precipitate will form. Moving on to the next type of problem. This problem, we were predicting whether or not a precipitate would form if we mix 2 solutions together. Now you're going to have 2 ions that are already pre-mixed with one another, and you will slowly add a third ion to it to determine which one will precipitate first. So, predicting what will precipitate first. We have a mixture of fluoride ions and sulfate ions. If we add barium slowly to the solution, which one of these will precipitate first? So, again, we have a container, we've got the fluoride ions, we have sulfate ions in here. We've got a device that allows us to add drop by drop by drop of barium 2+ ions. What our question is, will BaF2 or BaSO4 form a PPT first? Which one will we see as a solid at the bottom of our container? All right, so we're going to divide our paper in half. We're going to write a chemical equation and a KSP expression for both of these substances. On the left, we have BaF2 in an equilibrium with barium ions and 2 fluoride ions. On the right-hand side, we have BaSO4 in an equilibrium with barium ions and sulfate ions. I then write my KSP expression for both. KSP is going to equal the concentration of the barium ions times the concentration of the fluoride ions, which needs to be squared. And then over here, we're going to have our KSP expression equals the barium concentration times the sulfate concentration. Now, we're given KSP values for both, and we know our initial concentrations of these different ions. So what we're going to ultimately do is we're going to solve for the barium ion concentration on both equations here. Plug in the values that I have. I've got a KSP. I'm going to solve for the barium ion concentration, and I have the fluoride concentration on that side. On this side, we're going to solve for the barium concentration, and we know the sulfate concentration. So I solve for the barium concentration on both sides. This side, it's going to be 1.7 times 10 to the minus fourth molar. On this side, our barium concentration is going to be 1.1 times 10 to the minus ninth molar. We then compare these two values. If we remember the arrangement that we had, we're slowly adding barium ions to this, determining which one of these will precipitate first. We go back and look at the numbers. Whichever one has the smaller of the two barium ion concentrations, that'll ultimately be what precipitates first. Rarely will you have to look at the coefficient. What you'll be focused on here are these exponents. Okay, -4th to -9th, this is 5 orders of magnitude smaller of a value. Therefore, the barium sulfate will PPT first.